Screen resolution. All right, right about time. Getting a little close. So I got two articles that I think are interesting to share here regarding ChatGPT. So let me make sure it's recording and share the screen. So this is all going to be recorded. All right, so it's getting recorded. So good. All right. So this is the first article. It talks about GPT, which is from OpenAI. The same company has a separate product called Codex, which is a AI engine for coding specifically. It can help people write actual code. So this article talks about how Codex won't replace developers, but I think it's going to change the nature of developers. In other words, a developer still needs to be able to analyze what Codex is outputting, because in case the AI outputs incorrect code or suboptimal code, the person should still be able to step in and go like, that code does work, but it's not the most optimal code. We can improve it like this, or I can test this code and make sure that it is working and so on. So it's not going to replace humans, and people still need to understand how to write code, and I guess even more so than before. And then there's another article that I also want to share. Give me a second here. Let me share the other one. This one is interesting, especially from your perspective. It is particularly interesting. Let me find that first. I don't remember where I put it. I sent it to myself, so I need to. Oh, there we go. Okay, so this one is. Oh, nope, that's not the one. Okay, give me a second. I really need to find this one because this one is particularly interesting. Dark mouth. There we go. Right. Okay, so this is the one. And let me put the link here. It doesn't affect this class as much as some of the other classes. And you guys have taken most of the programming classes already on this campus, so it's not going to affect you nearly as much. So this is coming from a CS computer science professor, discovering that many students, like more than a third of his class, were turning in code that ChatGPT generated in one of the assessments. I cannot remember whether it's an exam or just homework. So eventually the professor had to move everything back to in-person and on paper. And the most interesting part from my perspective is how some of the students did not think there is anything wrong with turning in code that ChatGPT generated. They did not see anything wrong with it at all. Now, in terms of ethics, in terms of whether this is moral or not, that's not up for me to talk about. Okay, so I'm not going to talk about that part. But my argument is, if AI can do your homework, AI can do your job. So that means, so what is your plan? Not you, but the people who think it's perfectly okay to turn in code that the AI generated. So the question is, what is your plan to get a job? How do you get through the interview process? So that's that. I was also reminded by some people that I'm not supposed to talk about job stuff. I should just focus on the SLO, the student learning outcome of the class, and not talk about, what you guys might be doing with what you have learned in this class and also your degree in general. So I would try to refrain from talking about the other stuff. Unless you ask me, because I can respond to your questions. I only need at least one of you. There exists one of you asking me that question, and that gives me enough reason to answer and address those particular things. All right, so I got some really good stuff for you guys. You're starting just from the get-go. Okay, so let's go with the good stuff first. So let me move this into the second monitor right here. And then I'm gonna do this. There we go. Once again, focus on the right-hand side, because it's already done. So, from a conversation with one of the students, came to my office and try to clarify with me, what does it mean when we say for all, and what does it mean when we say there exist? So this is it, okay? Another way to look at quantifiers is we basically have to first define the big and the big or operate. They're kind of like sigma, okay? They're kind of like a sigma notation. So if I say big and E in 1, 2, 3, big P of E, it really just becomes a P of 1 and P of 2 and P of 3. Is that okay? Does everybody kind of understand that notation? All right. And then there's another one for big or, which means we are, instead of doing the and, we're doing the or. So is that part okay? I mean, let me point to which part I'm referring to. So are the definitions of the big and the big or okay at this point? If they are analogous to the for all, I mean not for all, they're analogous to the summation, the sigma notation in mathematics. So we're good? All right. So once we have these two things defined, then we can redefine for all E in X, P of E to be exactly the same thing if and only if, one is true and then we use the big and notation, E in X, P of E. They mean exactly the same thing. So you basically just end up with a big, long and expression where P is applied to every single element and you're ending the whole thing together. Is that okay? So if any one of these, if any element in X is going to make P of E false, then the entire conjunction is going to be false. Otherwise, it is by default true. So this is the one of the examples. For all I in the empty set, I is less than 0 and I is greater than 0. This entire quantified expression is actually true because the set that I'm focused on is the empty set, and by default for all has an answer of true. So the other one is there exist. So exist becomes something like this. There exists E in X such that P of E is true. Okay, this is my little editing thing. I forgot to use uppercase left, right arrow. So if and only if false or blah, 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 okay? So that blah, 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 blah is really just, saying, for every element in X, we want, to evaluate P of E, and all of those P of E's are ORed together, which means if at least one of them is true, then the function is going to be true. So we are looking for just at least one of those elements making P of E true. If I can find one element like that, I'm done because the whole thing is going to be true. On the other hand, if you try to apply that to the empty set, then by default, it is false because there's nothing to evaluate. If there's nothing to evaluate in the case of the existential quantifier, the default answer is false. So I just want to give you another way to look at the quantifiers because this may click better for certain people. So pick whatever interpretation that's easiest for you to understand and connect with other things that you already understand. So that's a review topic. And then we move on to bijection, which is really just a reminder of what bijection is. Start with a function. So bijection does not apply unless you have a function to begin with. Then we can say it is a bijection if and only if each element in the domain maps to one and only one unique element in the codomain And on top of that, all elements in the codomain are mapped to. So that's kind of like an English description of bijection. That's something that we talked about already on Monday. I'm just, this is just a quick review of the things that we have indeed already talked about. So are there any questions at this point? No? Okay, we're good. All right. So now we're going to start with new material. So I'm going to refer to the aleph null module because we are done with bijection. Okay, we were done with bijection in the previous class, which is on Monday. So today we're going to start with aleph null, and I'm hoping most of you had a chance to kind of at least get started with the aleph null module, because even though the concept seems to be simple, it does require quite a bit of processing in order to understand how things are mapped. Okay, so I'm going to start with this, and then we'll switch back, to the module. So aleph null, which is this funny symbol here, is defined to be the cardinality of the set of natural numbers. And that by itself is confusing. Yes?
Do the bars mean absolute value?
That is it looks like absolute value, but in this class, in this context, because it is operating on a set, it is cardinality, which is the number of elements in a set. So notations are extremely important. So by now, you should know your notations, okay? Because that's a knowledge thing. It is not even an understanding thing. It's just a knowledge thing. So it's really important that we have all the definitions, all the symbols already cleared up and understood by this point. All right, but this is the definition of aleph null. Okay, it is the cardinality of the set of natural numbers, which by itself is totally confusing, because how many natural numbers do we have? It's an infinite number, right? Because the moment you say, I think this is the last natural number, then I will ask, what is this thing plus 1? Okay, that's another natural number. So there you go. Okay, so there's an infinite number of natural numbers. How can we assign, a symbol to represent, the cardinality of the set of natural numbers? And what is the purpose of doing that? That seems like a totally worthless exercise. So yes, I understand that probably is the feeling of most people, but we'll get into the point of why this is important. So the next thing we want to say is, well, if you give me a set of X, how do I establish the equality over here? In other words, if you give me a particular set of things, and can I answer the question of whether the cardinality of set X to be the same as aleph null or not? That's a question, okay? It's like, how do we check that? So the definition of this equality here is you have to be able to find a function f that is mapping from this X here, which is a set, to the set of all natural numbers. And we also need f to be bijective. So that is the whole reason why we have to talk about bijection. And if we need to talk about bijection, we need to talk about injection and surjection. And in order to talk about injection and surjection, we have to talk about functions. In order to talk about functions, we have to talk about tuples and the Cartesian product. In order to talk about that, we have to talk about the set notation. That is a long chain of concepts leading up to what we are talking about in today's lecture. So I do want to give you kind of like an overview of how the concepts relate to each other, because the more you can connect between the big items, in an overview, the more you can understand the details. It's easier to kind of hold on to the details that way. So the first these are questions, okay? Z, what looks like a funny looking Z, refers to the set of all integers. So the question is, I wonder if the number of integers in the set of integers is the same as the number of natural numbers in the set of natural numbers. So instinctively, you would say no. Why? Because the set of natural numbers is a proper subset of the set of integers. Every natural number is an integer, but not the other way around. So you automatically go like, they cannot be the same. But remember, that is not how we define the equality of the cardinality. Okay? I'm not asking you whether one is a proper subset of the other one. I'm asking you whether the cardinalities are the same. So those are two different questions in this case. Okay, so we have to kind of make sure that we understand those are two different questions. So we'll start with that. And the way we do this is to go back to, I'm looking for the right window that has, oh, okay, just past that one. Okay. Sorry?
The related stories.
Oh, this one? Oh, related story. Stands for make out is more likely than you think. I would have no idea. I would have no idea. You know, in case you want to know why I would have no idea, you have to look up the lyrics of a Pet Shop Boys song called "I Don't Want It." So I'll point it out, and you guys can look it up later. And it is from the Pet Shop Boys. So I'm not going to play that song because the moment I play that song for 5 seconds, I will get a notification from YouTube saying that I have infringed on the copyright of a registered song and blah, 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 blah. So I don't want to get into that trouble. Yeah, but they will still flag me and then I have to explain. Yes. Yep, the lyrics of this song explains why this question is irrelevant to me. Yes. Okay, so let's go back to the notes here. As you can see, I can get distracted pretty easily, so I need someone to kind of keep me on track. It's like, heck, go back. Reminds me of a Sifu in Kung Fu Panda, who would say, focus, focus. Yes, that by itself is also a distraction. All right, so we're getting into aleph null. Okay, so this is important because I really want to make sure, I know most of you get this already, but I want you to know where the link is, okay, for the material that we are talking about. It is basically just sequentially going through the links in Canvas, unless I specify otherwise, because occasionally I do want to kind of change the order a little bit, but most of the time it's really just a sequential order. When we're done with one topic, move on to the next one, and then move on to the next one, and so on. So this is about aleph null, and we are trying to answer the question of whether we can find a function f going from the set of all integers to the set of all natural numbers that is bijective. So there are many functions, okay? Because all this says is, can we find at least one function to do this mapping? It doesn't mean that, oh, there's only one function that can do this. There can be an infinite number of functions that can do this. I just want at least one, okay? So if I find one, I'm good. So the one function that I have found that can do this turns out to be this, okay? So this is a typical definition of how you would define a function. F of x is, x is greater than or equal to 0, question mark, 2x, colon, in parentheses, negative minus 2x minus 1. Okay, what does it do? Okay, well, you can feed it certain values. The best way to test something like this is a spreadsheet. Because you can do this by hand on a piece of paper and you go like, really? Oh, I can work out 1, 2, 3. Okay, I'm tired. Okay, but if you use a spreadsheet, you can actually kind of generate a longer list. Then you can see the pattern. Okay, so I'll give you an example. Okay, what is f of -1? So you plug in x to be -1. -1 is greater than or equal to 0 is false. So this is a ternary expression, which means we go for the last expression. Remember, x is -1. 2 times -1 is -2, but the negation, arithmetic negation of -2 is positive 2. 2 minus 1 is positive 1. So we just mapped a negative integer to a natural number. Is that okay? So if you observe the pattern itself, what this is doing is it is mapping each natural number to even numbers as a natural number, and then it's mapping all the negative integers to odd natural numbers. Is that okay? So the way we are doing this, you can sort of look at it this way. So if this is 0, okay, and this is the number line, so from your perspective, these are the negative values, these are the positive values. So the way the mapping is doing is for all the numbers that are non-negative, we just space them out a little bit, okay, every other, so we leave here behind gaps between those numbers. And then for each one of the negative integers, we fit them into those gaps. So that's how this particular function gets the job done. So it is a function that can map from every integer to a natural number. So that is given already. Next is the injective. In other words, if I give you two different integers, can we guarantee that they map to two different natural numbers? What do you think? So you can try to prove that, okay? There are two cases that you need to prove. So first one is, what if you have two negative values? So if you have two negative values, they're both going to go for this one. And because the x's are different, so negative 2x minus 1 would also be different. It's just intuitive that when you have x1 and x2 and they're different, minus 2x minus 1 will give you two different values. Does that make sense? Okay. The other one is, what if I start with two non-negative integers as the x? Then you go for this one, right? So if you have 2x for one value and 2x for another value that is different, the two x's, it would be different. So the next question is, what if one is positive and one is negative? Okay, if it's positive, it's going to be like this. If it's negative, it's going to be like this. One is going to be an even number. The other one is guaranteed to be an odd number. So now we have handled all of the cases. Okay, I mean, intuitively. I mean, I didn't give you the rigorous proof in this case, but intuitively, we can think like, okay, each integer is mapped to a unique natural number. So, but there's one extra requirement to be a bijection, meaning that, all the natural numbers have to be mapped to. So the question is, can I find a natural number that is not mapped to using this particular function? There's no integer corresponding to the natural number. Can I find a case like that? The answer is okay. The answer is no, because we can have a reverse way of doing this. Give me any natural number, I can tell you which integer maps to it. All right. So the inverse function is right here. So this is the inverse function. If you give me a natural number, I can go through this to find out which integer maps to this natural number. It does exist. So now we know this is a bijection. F itself is a bijection. So let's check out how this works. We'll do it kind of quickly. So let's say that you're given the natural number 5, okay? And we want to find out what integer maps to the natural number 5 using F. So F inverse is going in the opposite direction. The first thing it wants to know is X even? It is, and it is not, right? So you have 5 mod 2 is not 0, so we go for the else, right? So over here in the else, we have 5 plus 1, which is 6. 6 divided by negative 2 is negative 3. So negative 3 is the integer that got mapped to the natural number 3. So if you give me any natural number, I can find out exactly which integer it was mapped from using F. So that's why we know F is bijective. Are we doing okay so far? All right, is everybody kind of somewhat comfortable with the ternary expression? Okay, it's actually really useful. Even in practical programming, it is more useful than most people give it credit for. Because you can, instead of using if then else as a statement in a function call within an argument, you can put a ternary expression to express the fact that, oh, in some cases, this is what I want to use as an argument. And in other cases, I want to use that as an argument. And you don't need to complicate the control flow of the program using a conditional statement. So there are many applications of the ternary expression. So because we can find such an f, it is bijective, it follows that we can claim that n, which is the set of all natural numbers, and z, which is the set of all integers, have the same cardinality. And we can now say that the cardinality of the set of integers is also out of null.
What if we throw it infinity?
Hmm? Infinity is not a value. It is a concept. It is not a value.
We don't deal with values. We don't deal with this concept.
You cannot plug in infinity as a value to try to figure out, the value of the expression. So we will see in this class later on that infinity as a concept is useful when you are dealing with limits, or what we call asymptotic, type of expressions. But it is not useful when we're trying to apply it in an expression, because infinity is not a value. I mean, in mathematics, it is not. In programming, interestingly, it is. So double and float actually has a representation of positive infinity, as well as another one for negative infinity. But in terms of actual math, it is not a value. It is a concept, but it's not a value. Okay. Any other questions? That's a very good question. Yep.
Wait, so how is it considered
There's no such thing as the concept of infinity in programming, because even when you're using doubles and using float double, or even the 128-bit version of your floating point numbers, I cannot remember what it was. It's a quad, because anyway, it can express a huge range of values, but there's still a limit to it, because you can maximize all the mantissa bits, you can maximize the exponent, and that's it. You cannot go beyond that particular value. So every single way you want to use to represent a value in a computer, there is a limit of what is the largest value that you can represent. So there's no such thing as the concept of infinity when you're programming, other than infinite loop, which basically means short of stopping the program, there's no way to get out of that loop. All right. So this one is tricky, right? Because we started off with a number line that goes in both directions. And then we end up saying, oh, by the way, they have the same number of elements. It's like, that is odd. That is truly odd, because one is actually a proper subset of the other one. And yet they have the same cardinality. Are we doing okay so far with that concept? All right. So the next one, let me go back to Joplin. The next one is, if you look at the Cartesian product between two sets of, between the natural numbers, is that Cartesian product itself also have the same cardinality as the set of natural numbers? This one is odd, right? Because if you look at this Cartesian product right here, n times n, it's basically a two-dimensional space. It's like the pixels on the screen, right? You got pixel 0, 0, pixel 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and so on. So we are now asking, when you have a two-dimensional space, okay, from your perspective, it's going to be this, okay? So if you have a two-dimensional space, and I'm asking the number of elements in this infinitely stretching two-dimensional space, is it really the same as just the natural number line, which starts from 0 and goes only in one direction? The answer is yes, yes. So the question is how, why? Why did we know it is the same? Well, we kind of know why they're the same, because according to the definition of equaling to out of null, we know that somehow there is a function f such that it can map the Cartesian product between natural number and natural number to just natural number. That is not difficult to find, okay? Because you can always say, okay, if you have the x and y coordinate, we'll just have x plus y as the function. But that would not be a bijective function. So the most interesting part is, how do we make that function bijective? Finding a function is easy, but making that function bijective is like, That's interesting. It's an interesting mental exercise to try to find that thing. Are we good so far with the concept or what we are trying to do? We are trying to find that one, at least one bijective function that can map n times n to just n. And we want it to be bijective. That's the most challenging part, is we want it to be bijective.
And do we know that function, or we're just assuming that there is a function?
Well, if that function does exist, then we know that these two sets have the same cardinality. Then we know the Cartesian product of n and n has the same cardinality as n itself, which is a very odd concept because now we are talking about dimensionality. Two-dimensional space somehow folds into one single dimension. The other one is just a number line. We are folding a number line that stretches out in both directions into a number line that only stretches out in one direction. I can see how these can be dance moves. Just me, explaining the number line concept. And also, for those of you who were in the assembly language programming class yesterday, the clock move. Yeah, okay. So maybe there's a future for me on the dance floor. You guys are all frowning. It's like, no, not gonna happen. I do agree, it's not gonna happen. Okay, so let's go ahead and try to find a function. Okay, so the best way that I can use to illustrate that concept is to use a spreadsheet. So let's go ahead and go to a spreadsheet, and I'll make it a Google Sheet here because that makes it easier for you guys to look at it. So let me sign in. Actually, don't have to sign in, because the drive is already signed in. It's just that the SSO is not. All right, so I'll put this into the shared drive just so that you guys will have access to it even now as I work on it. So I go to CISP440, go to the shared folder, and I will create a Google Sheets and name it in today's date, okay? Because that's a really easy way to come up with a unique name that is easy to find. So today is 2023-020-8. And now we are going to create that, two-dimensional space. So in the past, I'm trying to use, the way that I would use when looking at the graph, kind of like this. But this time I'm going to look at it, in a different way. So I'm going to look at this as 0. Okay, I'm assigning a value of 0 here. And then what I'll do next, I just have to find out. Yeah, so we'll name this one 1, this one 2, 3, 4, 5, 6, 7, 8, 9, and so on. In other words, I'm filling up the space in a diagonal way. When I'm done with one diagonal, I move on to the next diagonal, then I move on to the next diagonal, and I keep increasing the number as I fill that space. That is the function. Is that okay? Does everybody understand? Nope. Okay. So, well, let me do this first, okay? Because I want to try to fit more stuff onto the screen. So I'm going to decrease the width of these columns to a reasonable size. And then the next one is going to be here. This is going to be 10, 11, 12, 13, and then 14. So I'm basically doing this in a sweeping fashion. I start off with a corner, then I sweep this diagonal line, then I sweep this diagonal line, then this diagonal line, and so on. I mean, if you want to, I can highlight those diagonal lines. Okay, so these two, control click, we go, belong to the same diagonal line, and I can fill the color with something light, okay? Because if it's too heavy, it's hard, it gets hard to read. So 3, 4, 5 belongs to another diagonal line, give it another pastel color. And then this is yet another diagonal line. Let's give it yet another color. And this is another diagonal line. Okay, so does that help? Does it help to kind of visualize what I mean by diagonal lines? All right. So the next one is going to be F1 is going to get the value of what? 15, 16, 17, 18, 19, 20, and then move on to the next diagonal line and so on. So are we good so far? Does everybody understand the general approach of filling in each square or each coordinate with a natural number? Okay, so this looks good. Question is it a bijective function? And I'm not going to try to prove it in a rigorous way. I'm just going to use an intuitive way to show that, yeah, it looks like it's going to be bijection. So the first question is it an injection? In other words, can two squares end up with the same value? No, because we are incrementing after we fill in a square. So just by that act alone means that no two squares should end up with the same value because we are not backtracking to a previous square. We're always moving on to a new diagonal line. And every time we move on from one cell to another cell, we're always incrementing the counter. Is that part okay? Is everybody reasonably convinced that this function is going to be at least an injection? Next question, are we going to use up all these squares? Can I leave some square theoretically unfilled if I use this approach? Nope, because using this approach, you can just say, what about this square over here? I bet you're not going to fill this square with a value, and as a result, the function is not surjective. Well, I just have to say, okay, I'm going to use up the rest of this class to try to fill this particular one, because to do it manually, it's going to take some time. But using the approach, eventually this square will end up with a value. Does that make any sense? So we now know that it is surjective. Okay, every square will get a natural number. Wait, I got injection, meaning that no two square would have the same number. And then we also got surjection, which means every square is going to have a number. It is a bijection. I found my bijective function. As a result, the cardinality of n Cartesian product n is aleph null. Is that okay? Don't you think that's kind of cool? It's like, oh, we found a pretty intuitive way to get this done. So the next question, which I spent a lot of ink on, okay, I should say dark pixels, is what is the actual function? In other words, now that we have the approach to do it, okay, so I call that function g of 0, 0 is 0. So in the spreadsheet, you can kind of look at this as coordinate 0, 0. And this one is 1, 0, and it has a value of 1. So, okay, I keep flipping between my windows, but I should be flipping between my tabs. I cannot remember the shortcut key to flip between the tabs. Do you guys remember? Is it Control Tab and then Control Shift Tab or something like that? So I think Control Tab goes forward and then Control Shift Tab goes backwards. There we go. All right. So you can see how in here, g of 1, 0, which is new toy, is our B1 here, and then g of 0, 1 is our A2 over here, and so on. In other words, it's just a labeling thing. Okay, there is a systematic way to do this. So the thing is, remember that question? I was pointing explicitly to this square here. Go like, I bet you cannot find the value of that one square. So I want to generalize, right? I don't want to have to manually fill in everything. So the question is, how do I generalize this? Now that question is not directly related to CISP440, but it is related in programming in general, which is how do you solve a problem? This is a problem solving thing. Okay, so if you look up any other textbook, they would just describe the approach and that's it. They will stop right there. But I'm going to take it one step further. I will give you a closed form formula to basically say, apply that formula to the X and the Y coordinate, and you will find the value that goes into that square. Is that okay? I mean, that's what we're gonna do. So if, click the wrong key again. So Control Shift Tab, there, nope, on the wrong window. Because I got a lot of window open and I still need to click and there we go. Okay. So when you look at this pattern here, go like, how can I turn this into a closed form equation to get this done? Yes, sir.
Where the numbers of
They are coordinates.
okay.
So the first of the two tuple is the x coordinate, which is basically telling you left, right, wise, where is the pixel. And then the second number in the two tuple is the y coordinate, which is telling you vertically which row it belongs to. You can look at the first number as the column number, and you can look at the second number as the row number. Both are 0 oriented. Yes.
So the domain element in this function, all the elements.
Okay, so the question is, so if I rephrase your question, would it be what are the domain and the codomain of this function? Well, that is already set up here. We want to prove this, okay? This is what we want to prove. And this is the definition of aleph null. So what we are trying to do is to find a function that maps the Cartesian product of n and n to n. So the domain is the Cartesian product of n, and then the codomain is n itself. Okay. All right. So let's go ahead and try to figure out, how to write that algorithm, because that's kind of what we do as developers and software engineers. That's what we do. So this would be an interesting thing to try out with ChatGPT, is to describe the way that we are quote unquote painting the two-dimensional space with numbers, and then ask ChatGPT to come up with an algorithm to do it. I would probably guess that ChatGPT will give you an actual algorithm, like a loop inside a loop, to go through all the columns until we get to the one that we want. But it probably would not be able to give you a closed form equation to do the same thing. All right, but that's just my guess. You guys can try out ChatGPT after class if you're interested. I would be interested in the result of that. All right, so now we are moving on to the approach. Okay, so the approach is when you get to see. Okay, sorry, need to do the control tab. So you're trying to figure out a pattern. Okay, can we see a pattern here? I can see a pattern. Every time we move on from one diagonal line to the next one, the number of squares on that new diagonal line is just one more than the one before that. Does that make sense? I mean, let's check out the observation here. The first one has 1, then we have 2, then we have 3, then we have 4, then we have 5, then we have 6, then we have 7. Okay, that is an observation. The second observation is, okay, if that is the case, that means this number here that is going to F1 SSL is going to be 10 plus the number of cells on the pink diagonal line, right? So it's going to be 15, right? And then after that, it's going to be 21. So I have seen, IQ tests as well as programmer aptitude tests that would just give you this particular series of numbers and ask you, what is going to be the next one? And you guys have figured out the pattern already, right? So this next one is going to be a 15. This is going to be 21. This is going to be 28, right? And then plus 8 is 36, and then plus 9 is 45, and so on.
I was thinking like when we were first plugging it in, factorial, is that the?
No, it is not factorial. So how do we get the 45? Okay, so let's try to figure out how we got the 45 here. 45 turns out to be 1 plus 2 plus 3 plus 4, plus 5, plus 6, plus 7, plus 8, plus 9. That turns out to be 45. So in other words, we're trying to solve here just for the base of the entire of the diagonal line. What we're trying to solve is something that looks like this. So let me go back to Joplin here. So what we are really trying to solve to reduce it into a closed form is a sigma notation that has the look of something like this. We are adding from 0 all the way up to some, that's actually our x coordinate. So adding up to whatever x is, and then each term that we're adding is really just x itself, not x, I itself. So we are basically asking, is there a quick way to get to this sum without really making a loop to add all the things? That's the question, okay? So what do you think? Some of you have seen this already. You go like, oh, I can actually recall what is the closed form. But for those of you who have never seen this, it's even better because we want to figure out mentally, how do we figure out this whole thing here? How do we use mathematics to solve this? How do we look at similarities and go like, oh, okay, there's a pattern here and there's another pattern over here and so on. So one thing we can figure out, okay, so I'm switching back to my notes here. So Control-Shift-Tab. So what we are going to do is to notice that once you expand that thing, okay, once you expand this thing here, you end up with something like that looks like this: 0 plus 1 plus 2 all the way to blah 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 to x. Is that okay? That's just a really pictorial way to start it out. So they are divided into two different cases. Okay, when x is odd, I go for this notation. When x is even, I go for the other notation. So this part here really just is a play of all the sigma notation. With this sigma notation, I'm breaking up the original sigma notation into two parts. But the two parts have exactly the same number of things. And so we're just doing like, okay, we'll just bring it up. The first one is from 0 to x minus 1 the whole thing divided by 2. And then the next segment is going to pick up from where the first one left off all the way to the end. Is that okay? I'm just chopping that the long segment into two halves and say, okay, we'll do one sigma for the first half and we'll do one sigma for the second half. They have the same number of elements to deal with. Are we good so far? Okay. And then the second one, when x itself is, because we are starting from 0, I mean, you can change the equation a little bit so you can eliminate the 0. But since we're starting from 0, so when x itself is even, we have an odd number of items to add. So when there's an odd number of items to add, I take the one smack in the middle of the entire thing, which is x divided by 2, and go like, okay, you stand by yourself out there. The rest, I can divide it into the first half and the second half. This is the one right in the middle. Is that okay? All right. So to explain the entire derivation is not the purpose of this class. So I'm gonna just go like, okay, there's derivation, derivation, derivation. And then at some point, I get to the point where the two are now unified. If you look at the second to the last line right here, whether x is odd or not, I still end up with x times x plus 1 divided by 2, whether it is odd or not. So I go like, well, in that case, why do we even bother with a ternary expression when whether the condition is true or not, it gives me the same expression. So this is when I just go like, okay, it's just x times x plus 1, the whole thing divided by 2. Is that okay? All right. So let me ask you this because I really am curious. For those of you who know about the closed form already, because you recognize from your high school or your previous math class, somebody actually told you this sigma notation ends up with x times x plus 1 divided by 2. Did they ever go through the derivation? Nope. Okay. Isn't that kind of odd? Because I personally really would need to know the derivation to be convinced that it works.
They would just say the Gauss story that came up with this. They would just mention the Gauss story that came up with this problem.
Which story?
class. He was in school intelligent. Professor wanted to punish him. So
Oh,
he asked him to add number from 1 to 100. And then he came to school and did it like right away.
I see, I see. Okay, but to me, I cannot teach you anything that I'm not convinced of. And the only way I can convince myself is to go through a proof like this. So that's why I show you the proof, and in your leisure, which I know you do not have, I think it is helpful to go through the derivation because this is algebra. Okay, this is not higher math in any way. It is just algebra. Yes.
I know we're gonna do proofs later. Is this like a good template to follow for proofs like for this class?
Well, the proofs that we're going to have to do in this class is a different type. So it's not an algebraic kind of proof. So, it's not going to be as helpful. But this is important to me because, I need to show myself that I can derive the actual equality before I can teach you guys about, hey, if you start with this, you can end with that. Okay. So let's move on. So now, okay, so now what do we have? Okay, so getting all the way back. Now we know, okay, let me go back to the spreadsheet because the spreadsheet is going to tell us what we can do now. So the spreadsheet is now telling me, oh, there's an easy way to compute all of these values. Everything on row 0, which is what this is easy to figure out. You just have to tell me where it is, in which column it is, and I can tell you it is just the column times the column plus 1, the whole thing divided by 2. Woo! Easy peasy. Okay. The tag, that's really just one single row. What about the other stuff? Well, as it turns out, the other stuff is not really hard to figure out because once you figure out the base of a diagonal line, the value of the base, everything on the diagonal line is just incrementing one after another. And the y coordinate of that thing on the diagonal line tells you how much you have to add to it. Is that okay? Let me say that one more time. The numbering of the diagonal line itself is the x plus y. So this is coordinate 0, 0, which means the sum of xy is just 0. It is diagonal line 0. This is diagonal line 1, this is diagonal line 2, diagonal line 3, and so on. So you will notice one thing. If you look at the sum of the xy of everything in the same diagonal line, they add up to the same value. Okay. This picture does not show that, but I can show you another picture that can show that. This is coordinate 0, 0. This is 1, 0. 1, 0. This is 0, 1. This one here is going to be 2, 0. This is 1, 1. And this is going to be 0, 2. So this is enough already. You can see how if things are in the same diagonal line, then when you add up the 2 coordinate itself, which is 2, 0 in this case, 1, 1 in this case, and 0, 2 in this case, they all add up to 2 in this case. Is that okay? So that is helpful because now we can say, if you want me to figure out, okay, so let me go back to Joplin in this case. So in this case, if you want me to figure out the g, because I'm just using g as a notation of the function that maps from n times n to n. So I have to give it a 2-dimensional spacing thing, which has xy here. So if you want me to figure out what is g of xy as a coordinate, I can at least find out this is in the diagonal line x plus y. X plus y as a sum identifies which diagonal line it is. Is that okay? All right. And then I can also tell you that if I define w to be x plus y, just for simplicity, this is just a notational thing. If w is defined to be x plus y, then I also know, okay, using notations here, g of w0 is I'm using a LaTeX notation here. It is going to be w times w plus 1, the whole thing divided by 2. All right, so let's just take a look at this particular sentence here and see if it makes sense and connects with all the things that we have talked about so far. I'm giving you a particular pixel, okay? It is at XY. Okay, I'm not telling you exactly which X and which Y, but it's just a general, okay? The first thing we identify is we know which diagonal line it belongs to, because when you add up the X and the Y, that describes which diagonal line we are talking about. Are we good so far? Okay. But once we know which diagonal line we're talking about, the base of the diagonal line always has a value that is based on the diagonal line number itself times that number plus 1, the whole thing divided by 2, because of the equation that we just worked on earlier. Is that part okay? No? Okay, so the last part, which is, I cannot remember what I just said. Huh? Okay, can someone remind me what was the last thing that I said?
We can go back most of
We could, yes. I have done that in the past. I think the last thing that I said was why the value corresponding to that base is W times W plus 1 the whole thing divided by 2. Was that kind of what you were asking? Why it is like that? Why does it equality mean? Okay, all right. So it really has to do with, okay, so if I go back to the picture, okay, and it is in the browser, okay, and go back to sheet 1 because that's where the values are. So we are looking at, so this is diagonal line what? Let's see, 0, 1, 2, 3. Okay, this is 0, 1, 2, 3, 4. This is diagonal line 4. This is diagonal line 5, 6, 7, 8, 9, 10. This would be 11. Okay, so we know W is 11 because everything in that diagonal line, including this thing, this thing, this thing, this thing here, if I add up the X and the Y, it's going to be what? 11? Yeah, it's 11, right? Okay, so from that, I can also know that this is just the value of this thing is 0 plus 1 plus 2 plus 3 plus 4 all the way up to 11. Because I know the number of pixels of each diagonal line prior to each diagonal line. Is that okay? So how do we know what is 0 plus 1 plus 2 plus 3 all the way up to 11? It would be 11 times 11 plus 1, the whole thing divided by 2, because of the sigma notation that we just worked out earlier. So let's see whether that works out or not, okay? So in spreadsheet, there's a quick way to get to the column number, because you can just refer to it as column, okay? But it's going to be 1 based, okay? In other words, this is starting, it starts counting from 1 instead of 0. So I have to subtract 1 so that it becomes 0 oriented. So now we have this, and then we have to multiply that with with column itself, because that's the actual X value plus 1, and then divide the whole thing by 2. This is supposed to be 66. Does that make sense? Yeah. In fact, I can now go look like this, and then I say, oh, I can just stretch this out and go like, everything now is computed, but they are exactly the same as before. But I can also stretch it out in the opposite direction to anything I want to. So I have found the closed form to figure out the natural number that goes to the base of each diagonal line. Is that okay?
So
All right.
it's just the base, not the entire thing.
Just the base, but it's a very good start. Okay. Yes.
So we only need the X value to calculate the numbers inside the diagonals.
Yes, because, well, okay. Yes and no. We only need the X number to figure out the value of at the base of each diagonal line. Because the Y coordinate is a 0.
Okay.
So that means your Y is not contributing anything. Okay, so now the question is, if I know this is 66, and I'm just going to pick out this guy over here, I know it's in the same diagonal line. So what would be the value at the square that I'm highlighting? It'll be 70 because it is 4 pixels away from the base, vertically speaking. Is that okay? So it is still belonging to diagonal line 11, but the y coordinate of this thing is 0, 1, 2, 3, 4. So plus 4 is how we got here from 66. Is that okay? So once we figure out the base, anything along the diagonal line, we just have to say, oh, what is your y coordinate? Add that to the value at the base of the diagonal line, and then you have the value of any pixel along the diagonal line. So that means if I want to look at the value of anything, going back to the derivation here. So I'm just moving on to kind of, it would be, okay, wait, where is it? Right here. So this is the actual closed form of the value at any pixel. It is x plus y, which is the w, which identifies which column it belongs to, which diagonal line it belongs to, times x plus y plus 1, which is our w plus 1, the whole thing divided by 2, plus the y coordinate of the pixel itself, because that is how many steps we have to move along on that diagonal line in order to get to the pixel that we want to get to. Is that okay? All right. Yes.
So basically, let's say you want to find out whatever one 13 2 is, for the 13 2 for what? You
Yes.
can find out exact.
It will you figure out what natural number should belong to that particular square. I have read all kinds of literature on this particular topic. No one came up with the actual closed form. No one bothered to, because all they wanted to talk about is the concept. But I think the process of finding the closed form is a useful exercise. Because this is why you are still better than the AI. Because I think the AI cannot solve this problem. Not as a closed form, it probably would do it as a loop, like a double loop thing, just to figure out the value in using a brute force approach. But to get to the closed form, I think the AI is not quite at that point yet. And it's not difficult. It really is just going through the process of recognizing patterns. It really is just recognizing patterns. So there's remember earlier what I said. Earlier I said that IBM has a aptitude test for programmers, where they would give you a sequence of numbers and ask you what is the next one. That's what they call a programmer aptitude test, at IBM, which is roughly, okay, I'm just saying roughly, translating to what we now understand as the IQ test, because programmers and software engineers should really score high in IQ tests, because this is what we do. We have day after day after day after day of training, okay? And with all that training, this stuff just comes natural. So that, so it's not a measurement of how gifted a person is. It really is just asking, have you done this a bazillion times? The answer is yes, I'm still employed, I'm still doing this. So IQ test is not reflective of a person's intrinsic intelligence. It really is a reflection of, do you do this for life? Okay, and I go like, yeah, I kind of breathe and do this stuff all day long. So just my view on this stuff here. But being able to go through all those steps, okay, to figure out the answer, I think is important. Are we doing okay so far? Because this is the whole thing about writing programs. Because for most people, if they're trying to solve this problem, they'll just do a double loop thing, and their program will take a long time. When you have a really big value for XY, it's going to take a long time to finish. But for someone who solved the closed form equation, bam, it's done. Okay, and that makes a difference. Okay, I think it does make a difference. All right, cool. Yes.
So would you say for like recognizing patterns and to be able to convert into the closed form versions, it's more like about practice versus like just general aptitude and just like you'll just only get better in practice, basically.
Yes, yeah. The more you have programmed and the more math stuff you encounter, it makes your mind more flexible. So the more you can generalize, new patterns that are coming in. So it's not about regurgitating the process that you have learned before, and you go like, oh, it's exactly the same thing, step 1, 2, 3, 4. It is more about you can make more connections between the concepts, and that's how you can solve the problems more readily. I can explain the same thing using a different analogy because I think this is important. I think it's really important for people to understand what I'm referring to. So if you think about car mechanics, okay, so there are car mechanics where they just read off their books, that has a troubleshooting guide like a flowchart. So they just read off the flowchart and then they follow the steps. So they follow steps. But there are also car mechanics where they actually understand chemistry, physics, and all of the more fundamental concepts with an internal combustion engine. So those people do not go through the diagnostic manual because they look at the symptom, they ask the question, okay, I know physical laws do not change. Let's hope they do not, right? And the symptom is indicative of this thing here, but the explanation is using physics and also chemistry. So now the question is, why am I not having compression? Do I have fuel? Do I have the spark? So they go through their mind in terms of the actual way that the internal combustion engine works. And then they trace their way back and go like, yep, I confirm we got spark. Okay, I have an equipment to confirm. Do we have gas? Do we have the right mixture of gas, air future, a mixture? Yes, I have something that can measure that. Then why are we still not having compression? Well, the only thing that is left is the gas. Did the gas explode? Okay, yes, it did. So where did it go? Why is it not building pressure? Well, because it's not being contained. Where is it going out of? Is it because the piston and the cylinder does not have a good seal? Or is it because the valve is opening when it's not supposed to? Or is it because the spark plug was not screwed in correctly and it's escaping through the threads of the spark plug? So that's the line of reasoning that makes a mechanic a good mechanic, as opposed to someone who's just reading through a manual. It's go like, step 1, do this. Step 2, do this. Step 3, do this, and so on. And I'm trying to explain all of this stuff here because this is basically trying to problem solve something without following a prescribed steps like 1, 2, 3, 4. Because it's not going to be like that, when you are trying to tackle a problem that's worth being paid for. Yes, there are problems where you can go like step 1, 2, 3, 4, but typically we do not pay those jobs very well, if they still exist. All right, so any questions about this entire process? No questions? Is anyone feeling a little bit depressed? No, I hope not. Okay. I think everybody is capable of doing this. It's a matter of whether you exercise every opportunity to solve problems in this way.
I'm still not too sure. So how did this function that we just go to the other formula connects to n cross n equals right now?
Oh, okay. So that's a good question. The question is, how is this equation related to? Oh, okay. Keep clicking the wrong thing, dang it. Related to it is in Joplin here. Related to this claim here. That's your question, right? All right. So now I'm going to do something in Google Sheets, okay? Because Google Sheets is a very good tool for visualizing things and experimenting with things and whatnot. So Google Sheet does not have G. So for those of you who were in my assembly programming class last night, I'm going to do about the same thing. I'm going to go to AppScript here and define G myself. Okay. All righty. So I'm going to say function G. It takes X, Y as my parameters. And all I want to do is to return, what is it again? X plus Y times X plus Y, oops, X times Y plus 1, the whole thing divided by 2 plus Y itself. Okay, so this is, I'm just replicating that equation that I worked out earlier, and I'm plugging into g of xy, and I'm defining that to be a new function in Google Sheets, so that I can use it now as a part of my spreadsheet. So I have to remember to save the project first, and then I can go back to this thing here, and I just need to work on the first one and say, I want you to give me the g value, and then the x coordinate is going to be the column number -1, because column is always starting with 1, and we want it to be 0 oriented. And then we also have to give it a row number as my y, but we also have to subtract 1 from the row number, because once again, the row number is 1 oriented instead of 0 oriented. You go like, it is 1. Nice. So now we go like, well, let's try it out, just the first 3 thing. Okay. What about the things that are not on the base of the entire thing? Okay, that seems to work out okay. So you can see the way I work this is not to replace the entire thing, because I still want to see the continuity of this is what we figure out manually. This is also what we figure out manually, and this fits within that path. So I still want the confirmation that, yeah, okay, I think it's still making sense. So right now I'm fairly confident that this is gonna work. So I just go like, okay, it doesn't let me go in both dimensions at the same time, but that's okay. We can do it in 2 strokes. Yeah, okay, it's not using my processing time, so I don't care. So the square that I keep pointing at and go like, I bet you don't know what the value is. 512.
That would take it.
Yep. So now we have the g function. So does that explain, how it is relating, how the g function is relating to the cardinality of n times n? Yes. Okay. And the best part is it is a closed form. In other words, I can now say copy and then scroll all the way down and across and then down some more and across. Oh, okay. I guess column Z is the last one that we have. I can stick it here and go like, what is the value that's supposed to go here? Paste. And we know what it is. Woohoo. Okay. So let me look at the time. Oh, we still got 9 minutes. That's plenty of time. Because 9 minutes is a lot of milliseconds. Yes.
So what? Like, I'm just curious. No. What was the point in this? Understand why?
There are some potential applications. I have never seen any actual application of this, but it illustrates the concept of aleph null. And the concept of aleph null is actually why this class is called discrete structure or discrete math, because continuous math, which is what you learn in calculus and linear algebra and differential equations, that's one side of math. But discrete math, basically works on sets where the cardinality is aleph null. Countable stuff, basically. Infinitely countable sets.
So is this just a means to show us how to prove the cardinality of n, and there's just more just sort of.
Well, okay, so everything, all the sets, that can be proven to have the same cardinality as the set of all natural numbers, there are certain common properties to all of those sets. And so, by knowing whether a set has a cardinality that is aleph null, we know, all of these things that we know is going to work for the set of all natural numbers will also work here. So we are trying to establish equivalency between the sets. Once we know that they are quote unquote the same from a certain perspective, then we also know certain properties would also apply equally among all of these different sets. Even though they look entirely different, but because they all share the same cardinality, then we know certain things still work exactly the same between them. So there is that. Okay.
So in this function that we do, so g of xy is the cardinality, is the is the Cartesian of n cross n, and then the actual value is n. That's how you're trying to prove it.
Correct. So in this case, the column number is 25, and then the row number is 159.
That's from n cross n.
That's from n cross n. And then the actual value that goes here is in the codomain, which is 17,179 in this case. So we have a closed form formula to figure that out.
Okay, that's good.
But it is the process of how I found the closed form formula is by itself, I think, important. It is not something that I can test because I cannot easily derive a test so that you guys will have to derive something. But it is nonetheless, something that is important for you to kind of understand. Yep.
So when you say the derivation of the closed form formula, you mean like the addition, like adding those summations?
It is everything. So in the notes here, everything starting from the beginning of section 5 and all the way to the time that I actually finished up with the closed form, that's me explaining how I figure out the derivation. Because this is actually my derivation. I did not copy it from someone else. So that's one thing. I know we are getting close to the end time of the class. We still got 5 minutes, which is also plenty of time. So the question now is, what about the inverse function? Because we said that this is surjective, right? If it is injective and surjective, it is bijective. If it's bijective, that means there's an inverse function. If I give you a number like 20,000, you should be able to tell me which pixel owns that number. So once again, you have the brute force approach of keep filling in the diagonal lines until you get to 20,000, or you can try to use math to solve it. So the rest of this particular slide, all the way from here, all the way to this part here, is the inverse function. Okay, now you can always skip all the way to the end and go like, oh, okay, now we have it. But I think it's important to follow the steps, okay, to make sure that you understand how it happens. Because the derivation does not use any higher math. Okay, it is really just algebra. The most difficult part about this whole thing is the quadratic equation. I mean, you guys have all taken math 372, 370, or 375, or something like that. Okay, some of you even got placed in the calculus to begin with. So you know the quadratic equation already. That is the easiest, that's the hardest part of this entire derivation. The rest is really just how to make connections, okay? You know where you want to go. You have some basic idea of the tools. How do you get there, okay? So I'm showing you the whole process, my own thought process of how the inverse function itself is derived. So will I quiz you, on the derivation? The answer is no, okay? On the other hand, is it something that might be useful? I think so, okay? Because otherwise I would not have put it here. I would just do the derivation and just give you the closed form, done, okay? But I think it is important to go through the process and understand, okay, this is how to make connection here, make connection here, and so on. Because the more you read how other people solve problems, the more tools you're building up in your own mind. So now you go like, okay, I got plenty of tools in my toolbox. Instead of having a hammer, and you look at the screw, it's like, boom, 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 boom. Okay, you look at a staple, you go like, boom, 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 boom. You go look like an application where you have to cut a board into half. You go like, now in your toolbox, you have 20 different types of saws, and for each there are 10 different saw blades, and so on and so forth. Then it makes it easier for you to take on the next job. So I hope that point gets across here, because when people look at this and they're like, I don't need to know this, I'm just gonna skip it. All right, so that is all the time that we have. But for your reading assignment, I would like you to finish reading this entire thing about aleph null, and then we're going to move on next time. Next Monday is going to be the review of the exam from the previous semester. So I would definitely suggest that you try your best to do that exam. Find out what you do not understand, or find out what you think is confusing. Bring those questions on Monday, and then we can talk about those things on Monday. Yes.
Why did you think?
Exam is gonna be 1 week from next Monday.
We'll cover hundred aleph now. This is the final topic in the exam.
Yes, aleph no is the last topic in exam 1.
Easy piece. There was some similar coding in the exam.
Hmm?
There was some coding in the exam.
But that's also based on our.
Yeah.
Yes. So try your best to work on the practice exam, what I asked last semester, because we do have 4 days.
Sorry
So
about.
do as much as you can, and then what you cannot figure out, or whatever question you have, bring those questions on Monday, so that when I go over the answers of the exam, you guys can bring up your question. Okay, one last question. Yeah.
Where'd you get that?
This sir, I buy all my shirts from
Wood.com. Wood.com.
Yeah, WOT.
Oh, I know what that is.
Okay.
Have a good night.
Thank you.
Yep, you're welcome. Yep.
You can go first.
Okay.
The mine's on class related speak.
Do you mind if I close the recording?
Yeah, sure.
Stop the recording? Okay. I'm gonna stop the recording.